In this episode, the tire. When it rains, to avoid losing its grip on the road, it pumps up to 6 liters of water per second. The air conditioner. It uses a very special fluid to capture the heat inside and expel it outside. The electric toothbrush. So that it doesn't electrocute anyone, it transfers the electric current without any physical contact. And the turntable. To read music in the grooves of a vinyl record, it transforms lumps and bumps into electricity. And that's how it works. We take things apart so you don't have to. It's essential that your car tires grip the road. When tire grip is lost, even for a fraction of a second, there's danger of an accident. When there's water on the road, the tire faces an extremely challenging problem. If water slips between the tire and road, direct contact between the two is lost. It's catastrophe. Or not, because the tire is specially designed to evacuate all this water. A tire is actually a spectacularly efficient pump. At 100 kilometers per hour, it's able to pump more than 6 liters of water per second in order to maintain contact with the road. Okay, but how does it work? The anatomy of a tire is simple, at least in appearance. This rubber donut is a complex combination of more than 120 different materials. Together, they provide flexibility, resistance, and grip. But what makes the tire a rotating pump, capable of evacuating a phenomenal quantity of water? The design of the tire grooves. There are 4 main grooves that make up the circumference of the tire. Then there's a whole series of smaller, perpendicular grooves. The empty space in the surface of the tire created by these grooves is what allows it to pump water out from under and maintain direct contact between its surface and the road. Moving forward on a wet surface, the tire pushes the water, which forms a wave in front of it. The wave barely lasts a fraction of a second. It's quickly crushed by the tire. This is the most dangerous moment. The water penetrates the grooves and fills the available space. If the water is not immediately evacuated, the tire could climb onto the water, lose direct contact with the road, and begin skidding. It's the pressure exerted by the car which transforms the tire into a water pump. Thousands of kilos of iron exert immense pressure on the tire, its grooves, and the water they contain. Water does not compress. The space it occupies in the tire flattens under all the pressure, and the water must leave. That's the job of the perpendicular grooves. They connect the main grooves to the sides of the tire. Water, pushed by the crushing pressure of the car, is violently ejected from the tire through the sides. 30% of the water volume entering the tire is pumped out. The other 70% is trapped in the main grooves during the short period of time when that section of tire surface is in contact with the road. When the car is traveling at 100 kilometers per hour, that time is a ridiculously fast 1/150th of a second. And that water, too, will be ejected from the tire, this time out the back. This is how, using the weight of the car, the tire is transformed into a fast and efficient water pump capable of evacuating 6 liters of water a second from under a car that's moving 100 kilometers per hour. With 4 pumps like these, we could fill 12 bathtubs in 1 minute. But careful now. The faster the vehicle moves, the less efficient the pump becomes. The faster the tire turns, the shorter the time it's in contact with the road. So it has less time to pump out the same quantity of water. During a torrential rainfall, in order not to exceed the tire's efficiency threshold, it's a good idea to slow down, just a little. At 100 kilometers per hour, the tire evacuates an impressive volume of water. 6 liters a second, 12 bathtubs in 1 minute, a pool in an hour. But only on condition it's not too worn out. When a tire is too worn, its grooves become less and less deep, and so less and less efficient. But thanks to the design of these grooves and the pressure of the car on them, tires in good condition are monstrously efficient pumps that deserve all our admiration. The air conditioner. It uses a very special fluid to capture and then expel heat. The air conditioner. It harnesses the characteristics of a very special fluid to cool the air around us. When this fluid passes from a liquid state to a gaseous state, it absorbs a phenomenal quantity of heat. And when it becomes liquid again, it releases this heat. In fact, to cool a room, the air conditioner captures the heat inside and expels it outside, thanks to a fluid's change of state. Housed in this heavy-duty box are everything the air conditioner needs to take on the heat and chill the air. The air conditioner sits partly inside and partly outside the house. Serpentine metal coils traverse both sides. They're filled with the magic ingredient, refrigerant. Refrigerants are a mix of hydrofluorocarbons, chemicals that easily go from being liquid to gas and absorb lots of heat while doing so. How? Time to open it up and find out. At the indoor end of the unit, a fan pulls in air from the room. The heat in the air is transferred to the refrigerant inside the coil. The heat-deprived air then gets blown back into the room, but it's much cooler. Simple enough. Hot air comes in and chills out as it blows across the frigid coils, then back into the room. But where does all the heat go? And how the heck does the refrigerant keep chilling even on the hottest days? The key is phase transition. At the entrance of the evaporator coil that cools the incoming air, the refrigerant is in its liquid form at 2 degrees Celsius. Because it's colder than the air from the room, it grabs a bit of heat out of it. But the refrigerant's ability to transition easily from liquid to gas will soon allow it to absorb way more heat. As it absorbs heat from the air, its temperature goes up by a few degrees, just enough for it to evaporate and become a gas. Evaporation makes it absorb a lot more heat. Now, it needs to get rid of all that heat. Enter the compressor, this black cylinder that makes all the noise when the air conditioner's turned on. It's this motor that pumps the refrigerant through the coils. As the compressor spins at 3,500 RPM, the refrigerant winds its way through the cylinder. The compressor compresses the gas. It is forcibly squeezed, boosting its temperature. The tiny hydrofluorocarbon molecules get closer and closer to each other and heat up as friction between them increases. By the time the refrigerant exits the compressor, it's under high pressure and extremely hot at 65 degrees Celsius. It enters the condenser coil that's surrounded by warm air outside. Warm, but not as hot as the so-called refrigerant. Since heat always transfers from hotter to less hot, the refrigerant, which is hotter, transfers its excess heat to the air. As it winds around the condenser coil, the refrigerant loses enough heat to condense, becoming liquid again. This condensation process releases even more heat into the air. Once again, the refrigerant has undergone a phase transition, but this time in order to release tons of heat. When the liquid reaches the expansion valve, the pressure eases up. With more room to move, there's less friction between the molecules, and the refrigerant regains its refrigerant properties. Now, at 2 degrees Celsius, it's ready to start the cool cycle again. Even on the hottest day of the year, the air conditioner can chill out. It takes the heat from inside and dumps it outside. That's because it's a phase transition specialist. A simple switch from liquid to gas allows the air conditioner to take the heat. And that's what makes it so cool. Next, the electric toothbrush. It transfers the electric current without any physical contact. The turntable. To read the music, it transforms lumps and bumps in the groove into electricity. The electric toothbrush. It's, well, electric. We use it near wet sinks, with wet hands, and mouths full of water, and no one gets electrocuted. The secret is a miracle of science, induction. Thanks to induction, electricity can be transferred from the wall-plugged recharge base to the brush handle without any electric contact. Cool, but how does it work? Let's sink our teeth into this smart, shock-proof device and the amazing technology behind it. How sophisticated can a toothbrush really be? Here are the components. The base that holds and recharges the brush. This model has an LCD monitor which counts brushing time and warns against excessive brushing force. It also displays the section of the mouth that should be brushed and the brush mode being used. The handle holds a rechargeable battery and the motor that drives the brush head. Now, some serious questions. How is it there's no risk of electrocution? How does the current travel between the parts of an electric toothbrush when they're all separable? How does the toothbrush know when it's time to change the brush or when someone is pushing too hard on their teeth? How is information transmitted between the brush, the handle, and the screen? How does the motor make the brush move, like a brush? First, the motor. It's packed inside the handle with the electronic circuitry, the battery, and the gears for the brush head. The battery is sealed inside the green protective case. It powers the motor, which spins at 10,000 revolutions per minute. Next step, movement conversion. The rotating motor spins a gear wheel. The gear wheel moves a crank and a drive shaft. These components form an ingenious mechanism, which converts rotation into linear movement. So, as the gear wheel rotates, the crank pivots the drive shaft back and forth on itself. This movement conversion makes the brush head rotate back and forth on the teeth. Rotation has been converted into oscillation. The brushing action changes for each brush head. But how does the system know which brush head is attached? Each brush head contains a radio frequency ID microchip. The chip identifies the brush head, so a massage head will start when the handle is in massage mode. The radio frequency ID microchip doesn't have to be in direct contact with the rest of the electronic circuits, so it's sealed, safe from water and corrosion. When the brush head is attached, the microchip is activated, and it communicates with the handle using radio waves. Radio waves transmitted from the handle provide the microchip with the power to perform its calculations. After a brush has been used for 3 months, the microchip sends a message to the screen that it's time for a new brush. A sensor monitors the pressure on the teeth or gums and tells it when it's too hard. Brushing force pushes the drive mechanism within the frame. Brushing beyond the specified force triggers a proximity switch, and a warning lights up on the screen. Pressure monitoring, radio waves communication, movement conversion. And the best is yet to come. The incredible technology that charges the battery even if the toothbrush is completely sealed, without any contact between the toothbrush and the recharging base. Inductive charging. The toothbrush and base form a two-part transformer. The base is one half of the transformer, and the toothbrush is the other half. The base contains a copper coil, and the toothbrush also contains a coil. Electricity flowing into the base coil creates a magnetic field. Proximity to this magnetic field creates an electric current in the toothbrush coil, recharging the battery without physical contact. That's induction, and that's what keeps things safe. The electric toothbrush. It's stuffed with gadgets and technologies that almost make our hands useless. But its most astonishing ability is the one that allows it to transfer electric current through a magnetic field instead of wires, recharging its battery with no physical contact. Engineers call it induction. We call it incredible. The turntable. To read the music, it transforms lumps and bumps in the groove into electricity. The turntable. Its needle reads music, pressed into the grooves of a vinyl record. In fact, the turntable's main purpose is to transform the microscopic hills and valleys inside the record grooves into electricity. The electricity is then amplified by an amplifier, and the speaker transforms it into music. For the needle, reading the grooves of a single record means traveling nearly a kilometer over microscopic bumps. As it sits in the record groove, the needle is constantly moving at incredible speeds. In order to transform the patterns in the grooves into electricity, the needle changes position up to 18,000 times a second. Okay, how does it work? The turntable, a record. The turntable motor, the tone arm, and the reading head, the pickup cartridge. It's here that a record's grooves become electricity. Once we start the turntable, its motor turns the record. When we place the needle of the pickup cartridge on the record, it follows the spiral groove along the surface. On each side of the record, the groove stretches half a kilometer. Since the record is turning, the groove slips along under the needle, which appears to stay absolutely still. But the groove is far from smooth, and the needle certainly does not stay still. The sides of the groove are crammed with tiny hills and valleys. Talk about subtle variations. Some bumps are 3,500 times thinner than a human hair. The tiny hills and valleys represent music that's been pressed into the record. And it's the turntable's job to transform these lumps and bumps into electricity. The pickup cartridge is where it all happens. There's only one way to really know how it works. That's to pull it apart. The needle, which is made up of two pieces, the cantilever, and at its extremity, the stylus. A magnet, copper coils, and conducting wires. As the record turns, the stylus continuously follows the hills and valleys in the groove. The stylus is incredibly busy, moving up and down and left to right. It changes position up to 18,000 times per second. The pickup cartridge transforms this rough ride into electricity. How? As the stylus bumps along, it travels with a magnet that's attached to the cantilever. It's also bouncing every which way. And that's actually what starts the process. A magnet emits a magnetic field. When the magnet moves, its magnetic field moves with it. The tiny hills and valleys of the groove, which represent music, are transformed into a moving magnetic field. The next step is to transform all this movement into electricity. That's where the copper coils come in. It's a process that happens naturally, thanks to an electromagnetic phenomenon, induction. When a copper coil finds itself in a magnetic field, and when one of these two moves in relation to the other, this movement causes an electric current to appear in the copper coil. The movements of the magnetic field cause the appearance of an electric current in the coils of the pickup cartridge. The electric current is an electric representation of the hills and valleys of the record groove, an electric representation of the music. The turntable has done its job. Now the electric current is amplified and sent to the speaker. The turntable is a virtuoso of precision. By ingeniously exploiting magnetic phenomena, it detects hills and valleys 3,500 times smaller than a human hair, which it then transforms into electric current representing music. Transforming tiny hills and valleys into electricity in order to read the music pressed into a vinyl record. That's a performance nothing short of spectacular.